Today we're going to learn about indicators, pH indicators, and we've used a lot of these, so it's not new information per se. I'm just kind of giving you way more detail than what we've done before. Okay, now with indicators, here we go. Acid-base indicators are used to mark the end of a titration. Get my highlighter. Okay, which for most points is the equivalence point. Okay, because if you think about it, it marks the end of a titration and it gives us some idea that the reaction has gone to completion. Okay, if our titration, our general form of our titration is M1 V1 equals M2 V2, and we're using it to solve for an unknown, that color change lets us know that we've reached the equivalence point, and then we can use that to do the math. Now, it only works if you choose one whose endpoint is the same as the equivalence point. So we haven't thought too much about this because I pretty much have just done it for us and picked something because I knew the chemistry. But they're usually very complex molecules, and they act as very weak acids. So they don't necessarily impact the chemistry. The generic form is just this HIN, where the IN stands for indicator, okay, with a hydrogen ion attached to it. So that's where we get that general form. And they will change colors when that hydrogen is removed. So when all of a sudden it needs to react, it will change color. Okay, so for example, phenolphthalein, which we've used a lot, this is the bright pink one that we've used to indicate when we've titrated something with a base. Phenolphthalein will turn pink once something reaches that base point. So for example, okay, here's the colorless acid form of phenolphthalein, and then once you pluck off the hydrogen ions, then we've got it's going to change color. Okay, so you've got your pink base form, which is just what's left. Okay, so you've got hydrogen here, hydrogen here. We may have lost that one too. Okay, so that's just the chemistry. Now, for general indicators, for example, if it was yellow when it was the weak acid was present, and blue over here, if more hydrogen ion is added to solution, the reaction will shift left to make it yellow. Okay, because if we add more hydrogen ion, which is a product, it's going to shift that way, so it will force it to go yellow. If more hydroxide is added to the solution, the reaction will shift to the right to make it blue. Okay, so just some different mechanisms. This is what's called bromethymol blue, and you can shift the color change back and forth. Here is the basic version. This one's easy because basic is blue, and then the acidic version over here as well. Now, how do we calculate the pH at the endpoint? Well, we assume the color change is visible to the eye when the ratio is 1/10. Okay, when that ratio is 1/10. So this just means that 1/10 of the indicator must have changed form. So it's a pretty small amount, meaning that we haven't necessarily overshot it. That's why we're always looking for the lightest color as possible, because the more color you have, the more you've overshot your titration. Using the Henderson-Hasselbalch equation and the 1/10 rule, the pH of an endpoint or color change, and we saw this with the pKa lab, that the pH is equal to pKa plus or minus 1. So it's very close, and we can use that because we know Ka values of weak acids, we know goals for pHs, so we can use that to our advantage. Now here is a chart. This one is in your textbook. This is not for you to memorize. The big ones that you will see, phenolphthalein, which we've talked about. Now this only shows where the color change occurs. So for example, phenolphthalein, everything out to this side is clear. It's clear, 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 clear. We start to get past neutral, which is 7. Once we get into 8, we get light pink, and then we get dark pink, and then it will just stay dark pink the rest of the band over here. Okay, and we've seen that, when we've done our titrations. Some of the other common ones, bromethymol blue that I mentioned, again, you have yellow when it's acidic. It turns green if you can get it right at neutral, and then it will be blue over here when it is, once it gets to the basic point. Some of the other ones that you may see, methyl red, methyl orange, but your book is going to ask you some questions related to these, and you can refer to that chart. I don't expect you to memorize this whole thing, but just have some general ideas. And so based on where you want where your equivalence point is going to be and what your goal pH is, you pretty much have a range of just about any indicator where you could pick from one of these in order to get your choice. Okay, so for example, The weaker the acid being titrated, the smaller the vertical area around the equivalence point. So this means less flexibility in choosing an indicator. For example, if we were titrating something with sodium hydroxide, and we're trying to get right at that equivalence point, there's some other options we could use. We could use methyl red. Once it would be red, and then once it was gone, we would have our equivalence point. Phenolphthalein, which we've used, is the opposite. It's clear, and then once we see the color change stay, then we end up with our equivalence point. So again, here is the weaker acid, so we have less flexibility. The phenolphthalein would be much better here for this one. Okay. For example, estimate the pH of a solution in which brome cresol green is blue and thymol blue is yellow. You just have to go back to that chart. See if I can get there. There we go. Okay, so you've got, just to show you how to read it, brome cresol green. We're looking for this one to be blue. Okay, so anything after 5, this is going to stay blue, all in this direction. And then thymol blue is yellow. Here's thymol blue. Okay, now thymol blue is interesting because it actually has 2 color changes. So it's red and then it's yellow through this entire point, and then once you get 8, it starts to turn green and blue. So the answer, where this one's blue and this one's yellow, is going to be anywhere between 5 and 8 for the pH. Okay, and so anywhere between 5 and 8, and then you have a 0.100 molar hydrochloric acid is made with 0.2 drops of methyl orange are added, is made, and then you add 2 drops of methyl orange. Sorry, what color is the solution? Well, it's red since the pH is going to be less than 3.5, so it would have that red color to it. Okay, so a lot of times if you're asked to explain indicators, you'd be given a chart like that. You'd be given number ranges, and you'd have to pick which one would be the best and when it would change color. Again, it's relatively, I think, fairly straightforward. Okay, I'm going to stop here, and then we will get into our last equilibrium, which is going to be solubility equilibrium and solubility products.